Hello AP Calculus, we've got a new video for you. It's the start of Chapter 5. We're going to be talking about intervals of increasing and decreasing, concavity, and inflection points here. Now, I am doing this video on the assumption that you guys watched the two videos already posted. Okay? So, this video is primarily for Charles. And Charles, happy 18th birthday. Sincerely. Hope you had an awesome day. We are going to just jump into example 7, which is listed on, it's page 190 of that Anton 5.1 homework attachment. So if you want to follow along with there, I'm going to slightly change the directions on this. So yeah, because they're a little bit wonky. I don't want to confuse us just by weird directions. So the directions that I'm going to put on here are pretty simple. Part A, determine the intervals of increasing and decreasing. Part B, oh, you can't see that at all. Oh boy. Yeah, pretty much. Part B, describe the concavity, concave up versus concave down. Intervals of concavity, a lot of times I'll just say describe the concavity. Describe the concavity. And then part C is give the x coordinates for the inflection points. Determine the x coordinates for inflection points. You know, the textbooks, it was trying to say like the largest interval by which one is happening, and I just thought, let's just keep it simple and do these directions, okay? Now, from the other videos, the intervals of increasing and decreasing can be done if you actually graph out the function, but what I want to do is show you exactly how you do that computationally. So, first thing you do, for increasing and decreasing, represent this first part. Now, if you recall, the derivative is basically the slope of the tangent line of a function at a specific spot. So, if you've got a function that looks like this, we can talk about how the slopes of the tangent lines are all positive as you move this way, right? And then there's a point at which the slope of the tangent line is completely horizontal. It'd be 0. So, slopes of the tangent line are positive, 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 positive. Then they go negative, 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 negative. Goes back to 0. Positive, 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 positive. So here's the idea. You can clearly see that this function is increasing as you move this way, and then it moves to decreasing as you move down, and then it moves back increasing in this way. The slopes of the tangent lines correspond with the increasing nature of the function. So when the tangent line slopes are positive, the function is climbing in its y value. When the slopes of the tangent lines are all negative, it's declining in its y value. So, if I were to take the derivative and determine whether or not the derivative is positive or negative, then what I can do is talk about intervals of increasing and decreasing. So let's take the derivative. F prime of x is equal to, I could expand this whole thing out, but I think I'd just rather use chain rule. Bring the 3 down, rewrite the middle, take 1 away, multiply by the derivative of x plus 2, which is 1. And since we're doing everything with respect to x, we don't have to worry about dx dt's or dy dx's or anything like that. So, we've got a derivative of 3 times x plus 2 squared. 1 times 3 is 3. We're done. Now, if you notice, back to our graph, these points right here seem to be the separators between increasing and decreasing. You could almost call them critical points. Those are the critical points. The places where the tangent lines are horizontal are the places where we're actually going to separate it through intervals. So we've done this a lot already. We've done this back in pre-calculus. It should be a smooth transition. So you first, to solve for the intervals of increasing and decreasing, you're going to set the derivative equal to 0. These will give us our critical numbers. And then you solve that equation. So I can divide both sides by 3. You get 0 is equal to x plus 2 squared. You can square root both sides. That gets rid of the square here. So you got 0 is equal to x plus 2. So our only critical number is going to be x equals negative 2. So here's what we do. We say negative 2 is going to be our stopping point, potentially, for where we might switch from increasing to decreasing or vice versa. So step 1, you find critical numbers. Step 2, set up intervals. Step 3, test a point in those intervals. So negative 3 here, 0 here, we would plug into the derivative, okay, because we're testing whether or not the derivative is positive slope or negative slope. That's what we're doing. We're testing the negative versus positive nature of the derivative itself. So if I plug negative 3 into this derivative right here, negative 3 plus 2 is negative 1. Negative 1 squared, positive 1. Positive 1 times 3, that's a positive value. Which means we're increasing. Test 0. Plug 0 in here. 0 plus 2, 2. Squared, 4. 4 times 3, 12. Also positive. Wow, okay, so this one wasn't like this at all. This one's saying our function is like hesitating at negative 2, and then it increases again. And it makes sense because here's what the graph actually looks like. It has a horizontal tangent line right there, but it doesn't change the fact that it slows down, stops, and then it goes back up again. It's increasing from negative infinity to infinity. So, intervals of increasing and decreasing. Part A, it's increasing from negative infinity to positive infinity. And that doesn't happen all that often. Let's talk part B, concavity. Concavity basically is talking about where we switch from concave up, which I think in the video, at least the way I've described it and the way the reading sort of mapped it out is it holds water, okay? It's sort of like right here. Right here is the separating point between everything is being pushed up here versus everything here is being pushed down. That's where the concavity separation occurs here. Right here is the point at which it seems to be going from concave down to concave up. So what we got to do is we actually got to take the second derivative, because the second derivative is actually very telling of how concavity works. So we take the derivative of our derivative. I don't think we have enough room over there. So part B. So remember, we are talking about this function right here. You can just bring the 2 down. 3 times 2 is 6. Take 1 away from the power, x plus 2 to the 1 power. Then take times the derivative of x plus 2. So again, we're going to find critical points where the second derivative equals 0. And this is interesting. The place at which concavity occurs is the same place at which we test for intervals of increasing and decreasing. So we set up the intervals one more time. Test a point. But this time we're plugging it into the second derivative, okay? So if you plug in -3 right here, you're going to get 6 times -1. That's negative. If you plug in 0, you get 6 times 2, which is positive. So what this is saying is, when I take the second derivative, negative means pushing down. This is going to be concave down from -infinity to -2. This is going to be concave up from -2 to infinity. And hopefully you guys make sense based on the graph that I put down here. It's like right here is the point that separates holding water down versus holding it up. All right, and then part C is basically an inflection point is just where concavity switches from concave up to concave down. So x equals -2 would be an inflection point. So part C would be x equals -2. Now here's what I'm going to do, guys. I know this video was maybe a little bit more haphazard than some of the other ones I've done, but based on the fact that you guys have 2 videos already behind you, I want to see how well we've got this and how well we can work through the problem set. So tomorrow, be looking for maybe some more examples online to help with that problem set. Please email me when questions arise, and maybe we can set up a Zoom meeting tomorrow if you need it, right around 9 a.m. or something. All right, thanks for watching. See ya.